Okay, good morning, and my name's Noel Matthews. Those of you who were at Bletchley, I think it was 2001, wasn't it, 3 years ago, I did a basic introduction to digital and made some comments on where I thought we should be heading for amateur television. What I want to do this morning is just do a very quick skate over the basics of digital, for those of you who missed that one, then have a look at what's been happening since then in amateur context, and I've got a couple of case studies, if you like, look at what's happened to GB3HV, and also to talk about the 70 centimetre test that Dave and I did getting on for a year ago. And then we're going to do a live demonstration of 2 megahertz wide digital on 70 centimetres. So that tells you what I've just said. I think the first thing to get our heads around is why are we bothering to go to digital? Why, when you talk about digital, do you then have to talk about compression? And to answer that first question, if you put a PAL analog signal into a straight A to D converter, you will end up with a bit stream which is 270 megabits, and that's what we know as SDI, and that's the current digital studio standard, and it's basically high quality lossless digital video. But 270 megabits a second is a lot of data, and approximately 33.3 megabits per second, and it's not really practical to transmit that. Even on some of our higher bands, we haven't even got that much bandwidth. So the obvious thing to do is to compress it. And back in 2001, I talked about the various standards of how we could compress it. But I think everybody's seen now that MPEG-2 has very much been adopted as the way to go. Although those of you who are keeping up with the press, companies like the one that I work for are now forecasting the demise of MPEG-2. MPEG 4 Part 10 is here, along with Windows Media Player 9. And we're seeing 50% gains on compression. Same quality, 50% less bit rate with some of the new compression formats. So the world is not standing still, but MPEG-2 is where we're at. And to be honest, as far as digital amateur television goes, I think we'll just keep it at MPEG-2 for the time being. Everything comes at a price. You can't start with 270 megabits and end up with 2 megabits without losing something. Ian's already talked about one of the impacts, and that is the delay. There is an enormous amount of horsepower going on in these compression engines to do that, and you end up with a delay. You end up with what we know as artifacts, which are things, nasty things that you see in digital pictures that you certainly don't see in analog pictures. I think I said at Bletchley, now when you're next watching Sky, don't look at the footballer, look at the grass and the crowds behind him. Then you'll really see what's the effects of digital compression, and you'll never want to watch it again. So, you know, it is better than, certainly these days, better than VHS quality, even at this sort of rate. The pictures generally look a bit softer, because one of the first things a compression engine does is it tries to reduce the hardness of the picture, because that takes more bits. And so you end up with a picture quality which is acceptable, and certainly for amateur television purposes, the pictures we'll show today, I would say, are acceptable. To give you an idea, some of the common rates, your typical news channel is going to be running down at 3 megabits today. Sky 1 is probably around an average of 6 megabits. I say an average because they do all sorts of clever things based on statistical multiplexing, such that all of the Sky services are put into one big data stream, and when one program needs more bits because the material is difficult, it will take them, and so there is never a constant bit rate on any service within the Sky programming. But the average is probably around a 6 megabits. Interestingly, I put that figure up at Bletchley and I said 8 megabits. That's the advances we're seeing in compression in the engines. They're getting much better. The required bit rate required for a given picture quality is decreasing all the time. And those of you who are satellite buffs who watch the feeds, typical news feed is at 8 megabits, 844, 8 megabits, but program exchange within the EBU network is done at 15 megabits. So that just gives you an order of scale. And there is the trade-off. The less bits you've got, the more delay, and the more likely you are on fast motion to see some of these artifacts. Audio, the great thing about digital amateur television is that it actually does the audio for you. I always have great trouble with audio. I know Dave does as well. Some of you are probably nodding as well. Audio always seems to come along second somewhere, but included in any of these coders is a couple of channels of audio for free. After all, it's only bits. And on some of the professional equipment, you can run up to eight audio channels. And what happens in the process is that the video is processed and compressed. The audio is also processed and compressed, but it takes a lot less time to do the audio compression. So actually we have to delay the audio to catch up, or so that the video can catch up with the audio. If you look at some of the dodgy news feeds around the world, you occasionally see lip sync errors, and that's entirely down to lip sync errors within the video compression. The audio is managing to creep out before the video. And all of that then is passed into an MPEG multiplexer, which puts together the video packets, the audio packets. There is then some wonderful stuff called service information, which is what tells the receivers which channel they're receiving. And in the case of when you've got a multi-program stream, like on Sky, it enables you to select between Sky 1, Sky 2, and Sky 3, 4, 5, 6, 7, 8, 9, 10. And that's all packaged together and produced as a transport stream, the MPEG transport stream, which comes out at 188 bytes. Now, one of the things, when you start to dig into this, you'll find people start to talk about different bit rates, and that's because the final output from the multiplexer can be of 1 bit rate, but of course the important thing for a lot of people is what is the video rate, and those two things aren't the same. The video encoding rate can be one thing, and because of all of the additional data we've had to add in, the final transport stream output is a different rate. So typically at about 5 megabits, a professional encoder these days will have about half a megabit overhead for a couple of audio channels, some service information, and null packets. So a couple of things there, probably just out of interest rather than of importance. So we've now got an MPEG multiplex, or a transport stream, which is just a big pipe of bits. And we then take it and modulate it. And there are three basic schemes which affect the UK. The first one is DVB-S, or DVB satellite, which in our case refers to QPSK, quadrature phase shift keying, and that's what we're showing today. There is also a DVB-C standard, which is the QAM 64 QAM 256 quadrature amplitude modulation scheme, which is used over the cable networks. And so NTL and TeleWest run that. The US, of course, went off and did their own thing with 8VSB. And there is another, they're all in the group of single carrier solutions. And there is one multi-carrier solution, which is DVB-T, or orthogonal frequency division multiplexing, which is, of course, what Freeview uses. And I had to change that part of the slide because it said on digital. In order of robustness, OFDM is undoubtedly more robust than QPSK. QPSK actually is a lot more robust than some of us thought it would be on multipath. But interestingly, one of the links here is dropping out, not because of signal strength, but probably because of the reflections around the room. And that's because we're running QPSK, which is a single carrier scheme, and is you can get, when you get reflections, if they're out of phase, they can cancel the signal and knock the signal down. So OFDM is certainly the most robust. QPSK and 8VSB are of equal merit. You won't find I don't think you'll find many people talking in terms of using QAM for over air, because that is the standard which was designed for cable networks. And of course, in a cable network, if it's engineered correctly, it's a very controlled environment with correct terminations. You don't get any reflections or standing waves. So QAM is the least robust of the schemes, but the upside of QAM is that the channel capacity or the payload can be quite large compared to the other schemes. With all of these digital modulation schemes, you're always trading payload for robustness and in some cases bandwidth. So that's the big difference between the different schemes. Single carrier versus multi-carrier. Oh, that slide didn't come out very well. I knew it wouldn't. Okay, what we're showing at the top is the whole concept of a single carrier scheme is that you've got one big carrier of which across the information is carried. And if you get multipathing or ghosting, which is out of phase, it will cancel that one carrier and you will get dropouts. The whole concept of OFDM, which Freeview uses, is that you've got a number of carriers within a fixed bandwidth. Each one is modulated at a low data rate. If you lose some carriers, it can then reconstitute it from the data that it is currently still receiving. And I just said that. The other thing to note is on a digital transmission, all of those schemes use error correction. The more error correction, the more robust, but the less payload. So you'll find people talking in terms of using a half FEC or forward error correction versus 7/8 FEC error correction. You get more payload, more bits with 7/8, but it's nowhere near as robust. Couple of important points. I think the two schemes we need to concentrate on for DATV are single carrier QPSK and multi-carrier COFDM. They're the two schemes that we would probably consider. The most important thing about single carrier QPSK is that the bandwidth varies with the bit rate. And that's pretty crucial because that's why we can get QPSK into 70 centimeters. If we're prepared to reduce the bit rate, and don't forget the bit rate affects the picture quality, if we're prepared to reduce the bit rate, the bandwidth will come in. And so what we're showing today is 2 megahertz wide, 70 centimeters, full resolution power with audio. We can only do that with QPSK because it's got the variable bandwidth. And I would suggest that it gives a DX mode. It's certainly, I think 2 megahertz on 70 centimeters is going to be a very interesting mode for us to play around with. And I did some very quick measurements, and by halving the bandwidth does seem to give a 3 dB improvement over most of the range that we'd be talking about. Sort of going from 10 megahertz down to 5 megahertz seems to give somewhere in the order of 3 dB. 3 dB is equivalent to doubling your power. We just heard the problems that we're all going to have with getting linear power amplifiers. So I think what we will find is that we will tend to operate at the lower end of the bit rates than at the higher end of the bit rates. Right, OFDM. I think there's some interesting experiments for us to do with OFDM, and it certainly is a very robust mode. There is a disadvantage for us, though, in so much as it is absolutely a fixed bandwidth. OFDM was designed as a PAL replacement, so there are 6, 7, and 8 megahertz versions of it. It was designed to drop into the band plans which were designed for PAL. The bandwidth is fixed. We can do other things within the OFDM window to trade robustness for bitrate, but the bandwidth remains fixed. So it's an interesting mode, certainly more robust under a bad multipath environment, but perhaps not quite so interesting for amateur television. That's a spectrum analyzer plot of an OFDM signal, and what you can see here is the 8 megahertz OFDM signal. that's 8 megahertz across there. If this was a laboratory shot across a piece of cable, that top would be flat. It would be noise, but it would be flat. What this is actually an OFDM signal where there is some frequency selective fading or multipath such that it's almost got a 0 dB notch. And don't forget, although you can't see it on the spectrum analyzer plot, the 2000 carriers are in here, occupying this space. And COFDM is so robust that even with that 0 dB echo in the middle, we're still getting fine pictures. The actual overall, there was no errors on the picture. So that's the benefit of COFDM. 0 dB notch, it can stand within the 8 megahertz. QPSK, not sure I should really show that. It's not one of the better QPSK signals, but it just gives an idea. There again, it's of a different shape entirely within, it's a single carrier mode being modulated on the sidebands rather than a distinct 8 megahertz pedestal.
10 dB per...
Yeah, so that's about 20 dB. Okay, so that was a very quick overview of the digital TV basics. And this really is a discussion of which modulation for DATV. QPSK is easier and cheaper. And the reason why I say that is you can go buy a Technomat receiver for less than £100 and it already covers 23 centimetres. So receive is relatively easy. QPSK in a chip, the generation is happening. This is my version of the German boards. That's the video encoder, and that's the QPSK modulator along with an up converter. So the QPSK is actually generated in a chip. There are similar chips available in the commercial market for COFDM, but the transmit design is a lot more complicated because not only do you have to watch the linearity, you have to watch phase noise as well with COFDM. And I think the biggest winner for QPSK for us, as I said earlier, is this variable bandwidth gives us the ability to have DX modes. So if we do consider those two, I think we need to come up with a band plan because it's no good having a number of different groups around the country transmitting on different standards because it won't be interoperable. Even if they're using QPSK, if one group is using 6 megasymbols or 6 megahertz, it's not going to be compatible with other groups running 4. And so I've put up as a suggestion some standards we could adopt. For 70 centimeters, 2 megahertz, half FEC. You'll see that demonstration in a few moments. For 23 centimeters, 4 megasymbols gives a bandwidth of about 4 megahertz. And that is a pretty good compromise between reasonable picture quality and reasonable robustness. For 13 centimeters, it would be interesting to try some COFDM. And there are, some of us have got access to some equipment and it is something we may be able to try. On receive, it's actually easier to do it from 13 centimeters because there are available MMDS down converters. You've probably seen them being used for the satellite the AO40 applications, which take in 2.3 gigahertz and give UHF out. One of those will go straight into a Freeview box at UHF, provided the oscillator is correct. But it will go straight into a UHF COFDM box and give receive capabilities for COFDM on 2.3 gigs. 3 centimeters or 10 gigs, probably go QPSK. It's, all you do is you take your Technosat box and put an LNB in front. So I would suggest we need to work over the next few months to come up with some standards that we do adopt, so that as repeater groups and groups around the country start to play with this stuff, we have a common standard. Right, so how do we get onto DATV? I think I've already touched on this. The first thing, as Ian said, you can't use your FM receiver. The great thing about this is that it just looks like noise. And so your FM receiver cannot be used, but 23 centimetre QPSK is easy. You need a free-to-air digital satellite receiver. Note of caution here, a Skybox will not do. No good getting a hold of an old Skybox. Sky have been quite clever in so much as those boxes are hard-coded to work only on the Sky transmission parameters and with the Sky service information. So you need to buy yourself something like the Technomate, which is a free-to-air satellite box which you can configure. There are some ex-commercial receivers around. In fact, the HV group has still got some, which come in at about £15 plus, or the Technomate is about £100. The other thing to note is that you will need a preamp. These are satellite boxes, and just like the FM boxes, when you've tried to use those on DATV or on ATV, you do need to drive them fairly hard because they're designed to be used with an LNB, which has got 55 dB of gain overall. So you end up with a scheme like this in the shack. From the antennas, hopefully you've got a masthead preamp, haven't we all? Yes, good. And you can either, if you buy yourself a Technomate, actually, you can miss off one of these, this isn't a plug for Technomate, but you can actually miss off one of these block diagrams because the Technomate has got a really nice feature in so much as it's got what's known as an L-band pass-through. So you can take your preamp, connect it directly onto the Technomate and feed your FM receiver through the Technomate. If you don't get one like that, you'll need to put your preamp into either a switch, literally, or an amplifier. And then just switch between your FM receiver and your digital receiver. So that's really all you need to receive QPSK on 23 centimetres. How to get on and transmit. It's a bit more difficult. If I was you, I'd encourage your local repeater group to transmit. That way you don't have to worry about doing that. You know, you've got a signal on air. Okay. The first way is ex-commercial kit. There are several of us around who've got some of this equipment. I actually work for the company who make this equipment, and over the last 2 to 3 years, there has been kit come available. The very first QPSK modulator, I hate to say it, but it was actually in the skip and it was raining, and I did go in the skip and I picked it out. This is professional. What we've actually got here, Sky are still running today. The Sky services use the equipment made by my company. This is a previous generation video encoder, and this is the QPSK modulator. So this produces the MPEG bit stream, the transport stream, which goes into the QPSK modulator. In this case, this QPSK modulator goes from 50 megahertz up to about 170 megahertz tunable. So yes, that's one way of getting on board. I've made equipment available to a number of repeater groups, and there is some around still if people are interested. The Worthing group have just got their license apparently, and that's going to be using some equipment. If you look on their website, it looks a bit smaller than this, but quite similar. The only problem with this stuff is it's big. You can't believe how big this stuff is when you get it into a normal shack. You can't believe how noisy it is as well. You know, your shack is very quiet compared to what the noise these things make, and they chuck out the heat, don't they, Dave? I think these early ones were about 400 watts. So you need aircon in the shack, and that adds to the noise. But ideally, that's repeater type equipment. You've then got the stuff that's coming out of Germany. And there are two basic systems coming out of Germany at the moment. One from a company called SR Systems, and another one from AGF, which is the Wuppertal University, which we've already talked about. Pardon me. The architecture is pretty similar, and it's a video encoder which produces the data stream which goes into the QPSK modulator board. The video encoder, by the way, uses a chipset from one of the Japanese companies. I think in this case it's Fuji or Fujitsu. And there's two chipsets, Fujitsu and NEL, and they're both available. And then the QPSK modulator is on a separate card. And I noticed that Giles, G1MFG, has already taken it and put it into a box. So some of you may like to go and talk to Giles about a system based on this stuff. And you get, that would give you an encoder and a modulator with a low power output. Just feed the output into your power brick, making sure that it's linear, of course, and taking note of all of the comments that have been said earlier. And I think, you know, this really for the average guy is the way to go. And, you know, less than the price of a decent PC, you can get on digital transmit. So that's really the way to go. Block diagram wise, it looks something like this. MPEG encoder, QPSK modulator is the bit that you buy from SR Systems or AGF. If you go down the ex-commercial route, you will then need to go into a sideband type transverter to get you up to your final frequency. If you go with AGF or SR Systems, you can probably bypass that because there is a mixer capability on board. So, really that's explained some of the technologies and how you guys can get involved. What's happening, as far as I'm aware, and I'd be really pleased if I've missed off some pockets of digital ATV activity, but I'm not sure. As far as I'm aware, this is basically what's happening. GB3HV has got a switched QPSK output. VR down, is it VR? RV, close. RV in Brighton has got a license for a parallel output on 10 gigahertz, so they're still retaining their FM output and got a QPSK output on 10 gigahertz. Ian Bennett, G6TVJ in Bristol, is doing some work on 23 SEMS. You've probably read his articles. Quite a number have been published in CQTV over the last year or so. He also has got some of these funny grey boxes from the Southampton area. Luton and Dunstable are... Yeah, on 13? Yeah. And Dave and I have done some work on 70, and obviously Ian is now in the Cambridge area getting involved. So there's a bit of activity happening. It's a bit in the south of England. I think our colleagues in the north need to get on board. Sorry?
There's Alan as well, who's got one of the
Yeah. Yeah. Okay, thought it'd be useful just to talk a little bit about what we've done on HV, just as a case study. So talk about this, and then we'll talk about the 70 SEMS demo. On HV, we've got the option to switch the transmitter into digital. We'll talk about the NOV in a minute. The point to note is it's under manual control. It doesn't do it automatically, and any time the transmitter is dekeyed, it will revert back to FM. We're running on the same frequency, 1308 megahertz, and it's a DVB-S transmission, QPSK, 4 megasymbols, 4 megahertz, half FEC. And the note there is that the NOV situation really does need clarification. I think a number of groups are pushing in this direction, and certainly as a... I don't actually hold the NOV for HV, so I can probably talk about it with impunity. I think it would be useful to have some clarity on this, bearing in mind that if you took the spectrum mask of the FM signal at 16 megahertz and the spectrum mask of a digital signal, we're well within our spectrum mask. So we're running just over 3 megabits of video. How did we do it? This was the original setup for GB3HV analog. The logic produced video output into a teletext generator, into an FM transmitter, power amplifiers, into the mast, into the antennas. We we thought it wasn't too bad. It could have been more difficult. The first thing we discovered was that HV runs, what's its, is it a VIC? Is it a VIC? VIC 20. Yeah, runs a VIC 20 and a Croppity test card generator. Okay, so they don't produce broadcast standard PAL, do they? So we then had to find a time-based corrector before we could drive the video encoder, because the video encoder is very fussy and said, I only want broadcast standard PAL. So we now come out of HV, out of the teletext, into the video time-based corrector, into an MPEG encoder, into a QPSK modulator, into an up converter. On the other side, we kept the FM transmitter, and we switch at the point of entry into the power amplifiers, but we've had to back off, for the reasons we talked about earlier, we've had to back off the digital when it goes over into digital mode. There it is in the HV shack. The piece in the 19-inch rack is the digital equipment. No members of HV here, is there? No. That's HV. That's the digital kit here. And that's the, those of you who don't know, that's Mike G8LES. Okay, and there's the rack. Now, what we've got here is, where's the finger gone? Time-based corrector into the MPEG encoder, QPSK modulator, same as that one, into a commercial up converter, which was a 1500 meg data transmitter, which has been backed off and modified for 1308. So I think we come out at about 100 megs out of the modulator and then up convert in this box. So, yep. Okay, so taken at home, that's a grotty picture from a grotty MFG receiver. Now that's, I think that's my look-through signal on an MFG in analog. Probably say that's getting on towards a P2. I think we're always a bit optimistic. And that is exactly the same system, but receiving digital. Yeah. Okay, thanks, Giles.